Hey everyone, today we'll be talking about non-asymptotic discontinuity and slant asymptotes, and we'll also make connections with rational functions. So let's begin here with our special case of discontinuity. A function is said to be discontinuous at x equals to a if it has discontinuity at x equals to a. For example, the function 1 over x is discontinuous at x equals to 0. In other words, asymptotes forms of discontinuity. But today we'll be talking about a special form of discontinuity, and that's point discontinuity. So we have our example here, and we can simplify our example by factoring the numerator and the denominator of the rational function. Once we do that, we can actually see that we have a shared factor at the top and the bottom of the fraction. We can actually cross these out, but we must remember that 2x plus 1 has a restriction on the whole function because it exists in the denominator. So we cross those out and we arrive at our new equation. Now we can graph. So we have a vertical asymptote, our horizontal asymptote, our point discontinuity. The restriction that was defined by 2x plus 1 actually constitutes the x value of the point discontinuity because the function is discontinuous or undefined at that point in time. We have our x and y intercepts, and let's see how the graph looks. We have our vertical and horizontal asymptotes. We have our graph in green, which I figure out the end behaviors using limits, and I also have a blue hollow circle which denotes discontinuity. Alright, let's move on to slant asymptotes. Until now, we've learned how to graph the vertical and horizontal asymptotes for rational equations where the degree of the denominator is greater than or equal to the degree of the numerator. But what happens when a numerator has a greater degree than a denominator? In a very special case where the numerator has exactly one greater degree than a denominator, such as this case, we get a slant asymptote. The very first thing we have to do is to divide the top by the bottom using long division or synthetic division. Here, the 22 that you see is actually the remainder. So the correct notation for this remainder in this simplified expression is to write 22 over x minus 3, which was the quotient of the original equation. However, 22 over x minus 3 is actually insignificant when you think about it. As x approaches infinity, or as x approaches negative infinity, this value gets very, very close to 0. And so therefore, it's not important, so we can actually cross it out. This new equation that we get, 2x plus 7, is actually the equation of our asymptote. So now we have a linear equation for our asymptote because the difference in degree of the numerator and the denominator was exactly 1. If this difference was, say, 2 or 3, then you would get a quadratic or, say, a cubic asymptote, and that would just make it more difficult to graph. But the idea or the concept still remains the same. Now that we have the equation of our asymptote, we can graph. We have several characteristics. We have a vertical asymptote at x equals 3 and our slant asymptote. Now, in order to figure out the end behavior as x approaches your 3 from negative and positive, it's very simple. You just use limits. But in order to figure out what happens as x approaches infinity or as x approaches negative infinity, if it's above or below your asymptote, it's a bit more difficult since this is now a slant asymptote. A great mathematician by the name of Methuselah came up with the concept that, remember that 22 over x minus 3? Well, if you sub an infinity or negative infinity to that equation, and if you get a positive or a negative value, that actually tells you if the end behavior of the graph is above or below. In this case, 22 over x minus 3, if you sub an infinity, you get positive, so it's going to be above the end behavior is going to be above your asymptote, and if you sub in negative infinity, you get negative, so it's going to be below your asymptote. Alright, the very last thing we have is making connections, and this is simply a real-world problem that uses rational inequalities. So when connected in parallel, a resistor of x ohms and a resistor of 1 ohm will have a total resistance defined by the function r of x equals to x over 1 plus x. Part A asks, for the total resistance to be 0.5 ohms, what does the resistance x need to be? We simply use rational equations, we multiply the denominator, and we solve for x, and x equals to 1. Part B asks, for the total resistance to be less than 0.25 ohms, what does the resistance x need to be? Here we set up our equation, but x has to be greater than 0, and that's just a given. In physics or in electricity, it doesn't make sense for anything to have negative resistance, so x has to be greater than 0. We solve our inequality as you would, and we get x is less than 0.33. However, since it has to be greater than 0, our interval would be x has to be between 0 and 0.33 ohms.